Okay, so thanks for your attention. This is talk about learning abstract concepts from multimodal data. So multimodal refers to different sensory modalities, and abstract in this context refers to like the difference between abstract things and concrete things. So abstract things are things that you can't really see or touch or feel or taste, and then concrete things are things that you can. So that's how I understood the term. So this is the first paragraph of the paper. I'm not going to just put the paper on the slides and read it out, so don't worry. The reason I put it there was because it's kind of interesting. If you actually look at how many of the words in that paragraph are abstract and how many of them are concrete, you can see that a lot of them are abstract. I didn't just like classify them myself. I took their concreteness from this is a sort of psychological study, ratings for 40,000 word concepts. So it turns out that at least in that paragraph, most of the words are abstract. And I only looked at nouns. Nouns are kind of, in some sense, the most concrete part of speech. So I thought, well, if the nouns are abstract, then probably, all of the words are, on average, more abstract. But then I thought, well, maybe it's just a domain thing. So I thought, well, I'll just check. What if I choose a really concrete domain? So this is actually concrete, the domain. I took this off a website of one of the world's biggest concrete suppliers. And it turns out that concrete, which many people would say is a very concrete domain, has, even in their literature, there's mostly abstract concepts. So, and then I did the British National Corpus because I thought that's a bit more scientific. And with the British National Corpus, about 72% of concepts in the British National Corpus that are either nouns or verbs, at least, are abstract. And when I say abstract, I mean more abstract than the concept war. So I just chose war as an example. Most people would think that's quite abstract. And on this rating scale, 72% of noun or verb concepts in the British National Corpus are more abstract than war. So basically, my point is, there's lots of abstract words in language and not many concrete words. Okay, why is that an issue? It's an issue because lots of people like doing multimodal semantics. So they start shoving in perceptual features into models that otherwise learn the meaning of words, and they notice that this starts to work pretty well. One of the reasons is obviously it's more information, so that makes sense. But also, it kind of models how humans learn, and since these things are evaluated on data sets produced by humans, it's obviously not really a surprise that if you're doing it a bit like a human in some sense, then you're going to perform better. Another good thing about this is that lots more of these multimodal data sources are available. So Google Images is a lot of images, and there are other things like that, including sound files and video and other things. So if you're mixing these things with language, you can get very high-performing systems. But there's a bit of an issue. Generally, these people that put these systems together, one of whom is sat at the back and did it very well this morning, they tend to evaluate their systems on very concrete concepts. So there's a bit of a question mark as to how much of language can you really apply the multimodal learning to, given that most of language is abstract, but these systems only seem, or the multimodal approach only seems to work well with concrete concepts. So that's the issue. Just to exemplify a little bit more, if you type dog into Google Images, you get a very nice kind of homogeneous representation there. That's a visual representation of lots of photos of dogs. And you can see that almost all of them have eyes, tails, ears, mouth, nose, and legs. So in terms of the features, it's a relatively stable set of a data source. And then if you do the same thing for evidence, it's really not clear what's going on. So there's no real common features there. And it turns out even statistically you can show this. So 2014, Keeler et al. ACL, they showed that if you type into Google Images abstract words, then the computer vision style vectors on average are much more noisy for abstract words than they are for concrete words. So that already suggests they're not going to be as useful. Just to go back to concrete, by the way, it does appear, at least by that metric, that concrete is definitely concrete because that's all kind of grey. So all of those images are the same. So the issue is most language is abstract. The other issue is multimodal models work very well. So how can we get multimodal models to be applicable to abstract concepts? Or is this even a useful thing to try? And then if it does it work for all abstract concepts or not? So in particular, I've sort of restricted the analysis to nouns and verbs because they kind of interact differently with each other in language. And if this is going to work, it's going to have to rely on concepts kind of interacting in language. So that's why we looked at nouns and verbs. So the way we did it, this well-known, very shallow neural language model from Mikolov et al. And essentially the model, as you probably know, stores input word embeddings and context word embeddings for every word in the vocabulary. And it just maximizes the probability as it learns, or at least if you train it in one way, as it learns, you just maximize the likelihood of being able to predict context words given a input word. So given the word word, you would have to pick all the words near it in that sentence there. And the model would be trained and the parameters updated to maximize the likelihood of correctly predicting one of the words near the word word. So that's the unimodal skip-gram model. So this is the multimodal skip-gram neural language model, which is just a slight enhancement, maybe, or extension of that model. So we do some joint training. We train on language exactly as before, and then we train, for a given input word, train the model also to predict perceptual features of that word. And the training examples are just interleaved. So it's kind of just joint training. First you learn from language, then you learn from the perceptual modality, and the ratio of this learning corresponds to the frequency of the words in language. So every time you see one of the words that we're going to put some perceptual information in for, you do the updates based on that. So you do the language-based update first, then you do the perceptual-based updates. And if you don't, if the word isn't a word that we're going to add in the perceptual information for, then there's only the language-based update, okay? It'll make a bit more sense in a minute when I kind of get a bit more concrete with my explanation. So, where did I get the perceptual information from? Well, I wasn't very clever about this. I just took it from a psychological study where people wrote down all of the properties of concepts. Now, if you know anything about this data set, it's a little bit like the McRae norms, which are maybe a more famous data set, but it's slightly bigger coverage. So it's a new data set from Cambridge. And what I did is, each of the features are kind of categorized in this data set into types. So I discarded the ones which were not really clearly perceptual. Okay, so you can see all of those properties of an apple, or taste them. It wouldn't have things like, is a fruit, because that's a bit too real world, and it's not just perceptual enough, right? So I've just taken the perceptual properties, and then there's another alternative information source, the ESP game, which is like 100,000 images annotated. The people playing the game wrote down things they could see in the image. So that's a slightly different perceptual information source, because when we train on this, well, we're getting the model to predict. So, for example, if we were updating according to the word tree, we would ask the model to predict words near tree, and in that case, that would be words that co-occur with tree in that image. So in this case, you're training the model to you're training concepts to get a bit closer to their features, and in this case, you're training concepts to you're training concepts to kind of get closer to things that they co-occur with, but in the visual modality. Okay, so what were the results? I don't know if results is the right word. It's kind of like findings, I guess. Not really trying to beat anyone with this work. Turns out we are trying to beat some people. So concrete nouns, it's very good for concrete nouns, okay? So concrete nouns, for these concepts, we had very good coverage, in fact, 100% coverage of the perceptual information. So the model reads the corpus every time it comes across a concrete noun. It does some learning based on the perceptual features of that concrete noun, then it does some learning based on the linguistic features of that concrete noun. And we've compared this to other ways of just mixing vector representations from two modalities. So obviously one of them is just sticking them together. So that's the red bar. And then another one is like CCA. So this is like looking for the canonical correlations between the features in both representations and then sticking them together. And then SVD is a standard dimensionality reduction technique, which you do after you've concatenated them. And then finally, our model. So this is the multimodal skitgram thing. So you see, it does seem to be a bit better at fusing the two data sources. And now there are many reasons why this might be the case. One of them is that there's a natural weighting here. So every time you see the concrete concept, you get a concrete update. So the concrete concept, you get a perceptual update and a linguistic update. If you see an abstract concept, in this case, you just get a linguistic update. So it kind of weights the modality, so you just get enough perceptual information which corresponds roughly to what a person might get. Because when they see a concrete concept, it goes in their eyes, but if it's an abstract concept, they don't get any perceptual input. So, so it turns out it's good at that sort of information fusion part of the game, but that's not particularly interesting because that's roughly what everyone had done before. So then the other thing is, well, that's the first conclusion. But the other thing is, what happens with the other concepts in the evaluation set? So in this case, we've still just put in perceptual information corresponding to concrete nouns. But what you can see is that it actually improves the performance of other concepts a little bit. So the dotted line is just a language-only representation with no perceptual input. And you can see that for abstract nouns, it doesn't work. So none of the three models that we tried managed to improve on the language-only representation. That's for abstract nouns. But for abstract verbs and for concrete verbs, the neural skipgram model does actually improve over the language-only baseline. So this is really interesting because both concrete verbs in this case and abstract verbs, they didn't have any perceptual information. We didn't put any features in. So a concrete verb might be something like kick. We didn't put any features in for kick. We just put in features for things like ball, perceptual features for things like ball. And through the interactions in the model, the representations for the verb kick has also improved. So the perceptual information seems to have kind of propagated through the model into the abstract representations. And that's true for abstract verbs as well. The way we do it seems to be a little bit better, at least for concrete verbs, it seems to be a bit better than the two alternative methods that have been proposed. I'll talk a little bit more about that in a minute. So yeah, it seems to effectively propagate information from concrete nouns to abstract concepts. There's an interesting effect here. If you look at the data sets, all nouns and all verbs, these are not just the concatenation of the pairs. So I should just say that I haven't explained exactly how this evaluation works, but basically we've got pairs in the USF free association norms, which are sort of a psychological measure of how associated two concepts are. And then when we take the dot product of our two vectors, we get a score of how similar our model thinks they are, and that's how the evaluation works. Overall, you get a correlation. So here we get a really interesting effect, which is that when we take the data set all nouns, this data set includes some abstract nouns with concrete nouns as a pair. Okay? And when you get pairs like that, our model seems particularly good. And the reason for that, I think, is that we generate in this model, you generate a fully mixed modality representation. So these features in the embeddings that come out of this model don't correspond, each feature doesn't correspond to a particular modality. Whereas in at least some of the other approaches, a concrete concept would look like this with linguistic features and perceptual features, and then an abstract concept would have the linguistic features and then would have some way of propagating to kind of infer new perceptual features. But the representation would not be totally mixed, so each of the features would still correspond to one of the two modalities. And of course, when you do one of these concepts, a dot product with one of these concepts, the propagated features have to be kind of consistent in the space with the actual features. And it seems like that sort of comparison isn't working very well. Whereas it's naturally kind of all aligned in one generally multimodal space, and so we don't seem to have the issues. That's why the performance on all nouns and all verbs is quite high, or at least that's the hypothesis. Okay, finally, there's a really nice kind of subtle observation about this. So there are some concepts, in particular abstract verbs, which actually get better. But they only get better in a certain, when you add perceptual information, but they only get better when in a certain case. So it's possible to add some perceptual information for these concepts. So the yellow bar is where I've added all the perceptual information that possibly exists. So in particular, for the ESP game, sometimes more abstract things are labeled in the images, and so we can still do some training directly from the perceptual modality. But then, the question is, do we include all this abstract perceptual information, which may be quite a bit more noisy, or do we just restrict the perceptual input to concrete concepts and then let it propagate through the model? And it turns out that the second one is generally better. So that's the blue bar. And in particular for abstract verbs, the only way to beat the language-only baseline is to restrict the perceptual input to just concrete nouns and then let it propagate through the model. And there you get a better score than if you actually go looking for perceptual features for abstract verbs. And probably it's because those perceptual features are very subjective, very noisy. They might not even mean anything. And that's also what we saw when we did the analysis with the vision models over Google Images, that often they're there's a very, very noisy signal coming out of abstract concepts if you try and get a perceptual information, if you try and get a perceptual vector for them. So it just creates noise in the model, and it stops the model learning well from language, which it should do. So basically, the moral of all of this is that it's good. You can learn some abstract concepts using multimodal approach, adding perceptual information into linguistic models. But you need to be careful about how you do it, and it probably makes sense to have a principled decision where you only add perceptual input for concrete concepts and then work on a model which propagates through to other concepts. So yeah, that's that conclusion there. Less is sometimes more when it comes to perceptual input. And a slightly clearer illustration of this, so this is the ratio of, this is just like now throwing in more and more perceptual updates relative to language. And you can see that concrete nouns it's okay for, but for others it really starts to tail off. So the perceptual information just adds too much noise. It's not as rich as the linguistic-only information. And so these concepts really start to degrade in quality. For example, once you get to 5 times more perceptual updates than language updates, you really get a case where none of these representations are very good anymore. So you need to mix language and perceptual signals well, and maybe a good way to do it is to roughly include one perceptual update for every concrete concept you see. That shouldn't necessarily be surprising because that's how humans learn, and of course these systems are evaluated on human data, so maybe that's not a coincidence, although I'm not going to claim that I know how the brain works. So yeah, that's all. One last thing while I'm here. This won't be published in a conference, so I thought I'd say it now. We've got a really nice new data set on semantic similarity, which focuses in particular on similarity and not relatedness. So we didn't evaluate anything in this work on that data set because it wasn't done. But it's done now, so we can redo the work on that. And if anyone wants real similarity rather than relatedness, then check out Simlex 999. Okay, thank you very much for listening.
It's time for questions. Time for questions, yes.
You have the correlation range is 0.3 out of 1 or out of what?
Yeah, out of 1, yeah.
Isn't it too low for considering?
Where's my? Oh yeah, microphone's here. Yeah, sorry, that is a very good point. So the correlation is low. So there's a number of reasons for this. So I mean, this is a state-of-the-art linguistic model that we're adding and building onto. So the fact is that on this data set, which we evaluate on the USF South Florida Free Association norms, even the very best distributional models get very low correlations. And the reason is, it's to do with how those scores are distributed. There is a very strange distribution of scores because of the way that data was collected. So it's just a hard data set to model. There are many, many papers that have been published in ACL and NACL and other venues where they evaluate on this data set. The reason it's popular is because it has huge coverage over a massive range of abstract and concrete concepts. So it's much more than if you just take previously what existed was WordSim 353 or something, which had 353 concepts, almost all of them were concrete. And you couldn't do this sort of analysis that I've done where you looked at abstract verbs and concrete nouns and things like that. So it was the best data set out there. I agree the correlations were low, but you know, I compared, so all of the, whenever we've got a comparison with another model, that contribution was published in a venue, and you know, people took it to be a meaningful difference. Obviously, there is some statistical arguments to say a correlation at that level, you shouldn't draw too many strong conclusions. But that's why, it's basically doing this work motivated us to create Simlex 999, which is a data set where models are scoring about 0.5. So the best distributional models are scoring about 0.5. So if I recreated this work with that data set, I think that everything would increase and the findings would therefore be a bit more robust. But previously, the data sets for evaluating semantic representations were really kind of like not necessarily put together in a principled way with the right range of concepts to be able to do this sort of analysis. So that's why you see there the correlation scores are a bit low. So yeah, I mean, in WordSim, people are getting, you know, there are models which will get, on this WordSim 353, there are models that will get like a 0.8 correlation. In fact, they're higher than inter-annotate agreement. So, yeah.
Thank you for a very interesting talk. I was just wanted to clear if I understood right. So you do not perform any perceptual updates for abstract concepts at all?
The only graph where we did that is the yellow graph here.
Okay, and that didn't help.
Yeah, exactly. So I did it as a sort of final experiment to see whether or not that might help. So this is a sort of, the yellow corresponds to a strategy of using all of the information you've got. It actually does help for concrete verbs. Mm-hmm. So with the ESP game, for example, you can extract useful features for concrete verbs. So that's something which is interesting. Yeah, and it may well be that, you know, for concrete verbs from images, you can, like, using proper, like, organic computer vision techniques, you can also do the same thing. And certainly from video as a modality, it's likely that you'll be able to do the same thing for concrete verbs. But certainly when it gets to abstract verbs, it's just not something really worth trying. You can't go directly from the perceptual modality to those concepts. You have to propagate it through language.
Yeah, that makes sense, but what about, your model has a mixed representation of features.
Right.
You don't know whether some certain element is a visual or a linguistic feature at a point, but would it make sense to initiate somehow just to concatenate, as they've done before, to concatenate the perceptual features, but initiate them randomly and then reevaluate this part of the vectors only when you have linguistic updates for the concrete concept, something like that?
Yeah, that's true. And actually, we're trying to build different models where, for example, we start with randomly initialized perceptual features for abstract concepts, and then try and infer them all together in one sort of, basically using a more like the neural network kind of paradigm of backpropagation and updating features, rather than kind of computing features in a sort of counting sense and then just shoving it all together, which is more the kind of traditional distributional approach. So we're trying to, I'm working on that at the moment, so hopefully we'll have maybe a more sophisticated model. Also, but maybe with a bit more depth to correspond to kind of the depth that the abstract, so a couple of levels, one with language and perception, and then another level where it might just be the abstract concepts together.
Quick question.
He's got quite a loud voice, so he could probably just shout.
Yeah, okay. So is it possible to use this in the other direction, in a sense that, let's say you run into an unknown language and you want to know the concreteness of a word that you have no idea, but let's say you have some images associated with those words. So can you use it to actually measure the concreteness of a word?
Yeah, so I'm very pleased you asked that question, because the answer is yes, and that's what we did in the ACL short paper. So it's something that my colleague Dow called image dispersion, but basically it's a property of concepts that corresponds to how varied the pictures are when you type that concept into Google Images. But equally, it could correspond to any image bank. So it's like the variance over the set of vectors where a vector represents a given image token. And that quantity corresponds or correlates very highly, very strongly with concreteness as rated by humans. So actually, yeah, if you want to automate this process, one thing to do if you've got banks of images is to first infer the concreteness strength from the variation in the images, and then to apply that knowledge of the concreteness strength to kind of weight to inform the parameterization or even the design of your model. Yeah.
Very interesting discussion, but I suspect we should leave it for coffee. So let's thank our speaker again.